All right, so we're gonna continue with ultrasound physics this morning. Um, we look at the, the some earlier properties of waves. We look at the wavelength. We look at the period. We look at the frequency. We look at the amplitude. The next property that we're gonna look at is the speed of a wave. Now we're just gonna go over what speed is. So when we talk about speed, we talk about velocity and we talk about just speed itself. And I've been trying to communicate to you guys, in physics and probably in life, we have scalar quantities and vector quantities. A scalar quantity is a magnitude without a direction, and then a vector quantity is a magnitude with a direction. You just think about it. You know, if you're walking down the road, you're gonna walk in a specific direction. You're not just even if you walk aimlessly, even if you don't plan to walk, you're gonna be walking in a specific direction. So if you give your speed and the direction that you're walking in, that's a velocity. So speed with direction is velocity. Whereas if you just give a speed, if you say I'm traveling at 30 miles per hour and you don't give any direction, that's a scalar quantity. So you need to understand those definitions, scalar and vector. Vector mean you have a direction associated with it. But speed is when you cover a certain distance in a time. So, you're driving at 30 miles per hour. So, at the end of 30 miles, it's going to take you 1 hour. Okay? So that is speed. 30 miles per hour. At the end of 30 miles, it's gonna take you 1 hour. So that is the speed. But you can get a little bit more technical because you can if you talk about instantaneous speed, which we don't want to get, I would want to confuse you, but you have to understand. I mean, these are relatively simple terms if you understand what you're doing. So the overall speed might be 30 miles per hour. So that at the end of 30 miles, it takes you 1 hour. But say halfway, at any point in time, you might be traveling, I'd say 45 miles per hour. And then at another time, you might be traveling at 25 miles per hour. Those point in time is what we call instantaneous speed. Just for your knowledge, but we're going to talk about overall speed, and it's actually a velocity because it has a direction. So speed with a direction is velocity. Now, if something is moving, it's going to have a speed associated with it, and hence a velocity. So speed is how fast an object is moving, and of course you're going to time it. Okay, so it is the distance traveled per time. Simple, straightforward. The definition of speed is not going to change, regardless what you're doing. It is distance traveled per time. Okay, so similarly, if you look at a wave, and you can pinpoint, or you can make up a point on the wave, and you can look at that point, and you can follow, if you follow it on the wave and you see what time it takes to move to a certain distance, then you can figure out the speed of the wave. All right, so again, if you say, for instance, you could put a little point on a portion of the wave and follow it, and you can see the distance that it travels, and you can time it. You can get the speed of that wave. But you don't have to be that complicated, you know. It doesn't have to be that complicated. What you should do, or what we do is, all right, so remember now, so you have a wave. So in your mind, just think of this as a uniform thing. So this is how we depict waves, right? All right, so this is a wave. All right, just in your mind's eye, think of this as a very uniform wave. All right, so we know, all right, so from one crest to the next crest is a wavelength. We've been saying that forever. All right, so from one crest to the next crest is the wavelength. And the symbol that we use for wavelength is lambda. So if you read any physics book, this is the sign you're going to see. Okay, so the distance from one crest to the next crest is lambda, and we'll measure it. Okay, all right, so we know the distance. We just need to know the time now, the time it's going to take from one crest to the next crest. But we know that too. We have been saying that that's a period. Remember, we said that's a period. The time it takes from one crest to the next crest, that's a definition of period. So remember the definition for speed, which is the same. So this is S. So speed is equal to distance. So the distance there is lambda. All right, let me just write it. Speed is equal to distance per unit time. Okay. All right. So if we apply the wave principle to it, the distance is lambda. That's a wavelength. Okay. And then per unit time, so we're going to divide by P. So that's a period, right? So for the wave, speed is equal to the wavelength lambda divided by the period, which is the time. But remember what we said about period? Period is inversely related to frequency. So this is the wave formula. And you need to remember this for the rest of your life. So the speed of any wave is equal to the wavelength times the frequency, lambda times f. So you need to know how it's derived, but you need to always remember this. Okay? So this is the wave formula. All right, so everybody should fully understand that. All right, so you understand the wave formula. No problem. And for metric units, distances in meters and time, time is in seconds. So we usually put it meters per second, or you can centimeters per second, but this is the metric unit, okay? All right. Another property of waves is reflection, okay? Another property of waves is reflection. That is, when a wave comes up to a boundary or an obstacle, it's gonna strike that boundary or obstacle. Portion of it is gonna reflect it backwards, whence it's coming, where it's coming from, and a portion is going to go through, and that's what we call the transmitted. So when a wave strikes a boundary, a portion is going to be reflected backwards, and a portion is going to go through to the other. Boundary separates two media. So a portion is going to go into the other media. All waves do that. Okay? So reflection, nothing mythical about it. It's just when a wave reaches the end of a medium or a different medium, it bounces off and reverses its direction. Okay? So if you want to draw that, remember, when you're doing this thing, you draw everything, okay? So if this boundary, if this is one medium and this is another medium, if you have a wave, say any wave, could be sound wave, light wave, regardless. When a wave strikes a boundary, okay, a portion is gonna be reflected. Okay. And a portion of the wave is going to be transmitted. Okay? So this is what we call the incident wave, the wave that's coming in. Think of this as a high. Oh my goodness. Anyway, this is a high, it's a new type of high. And then this is a reflected wave. It's donated by R. And then this is the transmitted wave. So I say nothing fancy. A wave coming in, it strikes a boundary, a portion is reflected, and a portion is transmitted through the other medium. So if you look at this as one medium, so so this could be air. All right, let's call this M1 for medium 1. And if you call this M2 for medium 2. Okay, this could be water, this could be hair, or reverse, or it could be blood and bone, or whatever. So when the incident wave, so you have a sound wave or a light wave, but we're talking about sound. So a sound wave travel through here, say it strike a tissue, heart tissue, whatever. A portion is going to transmit it backwards, and a portion is going to go through the heart tissue. It's going to continue to travel through the heart tissue. So all waves going to observe this principle. So, and not only it's going to observe this principle, but it's going to observe a principle called the law of reflection. That's a physics law of reflection. The law of reflection states that the angle of incidence, so the wave that coming in towards and strike the boundary is the incident wave. The law of reflection states that the angle of incidence is equal to the angle of reflection. Simple thing. What you do, where the incident wave strikes the boundary, you draw a perpendicular. So that's a 90 degrees. Perpendicular is 90 degrees. So you draw a 90 degrees angle, and the angle of incident is from where the incident wave, the angle that the incident wave makes with the perpendicular. So this is the angle of incidence, this angle right here. Okay. So the law of reflection said that this angle right here is going to equal to this angle. So this is the angle of reflection. This is the angle of incidence, I. And this is the angle of reflection. Okay. So this is the law of reflection. So when this wave, incident wave, comes in and strike the boundary, it's going to be reflected. It's not going to be arbitrarily reflected. It's going to be reflected following the law of reflection. So the angle of incidence is going to equal to the angle of reflections. This angle here is going to equal to this angle. Remember, a portion of the wave is going to be transmitted through the other medium. So when the wave is reflected, it bounces off the boundary. It remains within the same medium. So it's going to transmit here, and it's going to bounce back and go there. So it's in the same medium, media one. Okay? So just think a little bit. All right, so when we're doing ultrasound, so we're doing ultrasound of the heart, and we send a wave out. Okay, we send a pulse. That's a sound wave, and we send it to the heart. It's going to travel. It's going to take a certain. It's going to travel a certain distance to the structure that we're looking at. It's going to bounce off that structure, and it's going to come back to the transducer. That's how we see it. So you see that the distance, when we talk about the distance, it is actually double the distance that it. So when you talk about distance, it's going to take it. It's going to travel a certain length to get to the heart tissue, and then it's going to travel that same length to come back to the transducer. So if you know the distance from the transducer to the heart tissue, the overall distance is going to be doubled, because it's going to have to travel to the tissue, and then it's going to travel back to the transducer. Okay? And you can do simple experiments. If you go to the Grand Canyon or any canyon, and you say you shout, so you shout and you hear the echo, So when you hear the echo in one of these canyon or whatever, the sound wave travels from your mouth to the wall of the canyon, and then it is reflected backwards to your ear. So when you hear your echo, what it is saying to you is that, okay, the sound is traveling a certain distance from your mouth to the canyon wall. It's reflected off the canyon wall, and it come back. It takes the same distance though. It is reflected off the canyon wall, and it come back to your ears, so you hear it. So if you know your distance from the canyon wall, and you double that, that's the total distance that the sound wave travels. And if you time it, say you start shouting, and by the time you hear it, if you have a stopwatch and you time it, then you can, if you put distance over time, you get the speed that sound travels in air. So you can, if you're doing straight physics, this is one of the questions that they would give you. So you can calculate the speed of sound in here. And the speed of sound in here is fixed. The speed of sound in any medium is a fixed number. You're not going to get the speed of sound in here. One day it's going to be 330 meters per second. Then the next day it's going to be 1,000 meters per second. It doesn't work like that. I mean, it can work like that, but for your purpose, it doesn't work like that. The speed of sound in a medium or a media is a fixed number. Okay? All you have to do is use a simple formula for speed, distance over time. Okay? The canyon experiment is a good experiment, because if you shout, your sound wave is going to travel from your mouth to the canyon wall. It has to be reflected off the canyon wall back to your ears for you to hear it. So if you know your distance from the canyon wall, you just multiply that by 2. And if you have a stopwatch and you time when you shout to when you hear it, that is the time that the wave travels to and fro. So you can use the simple formula, speed is equal to distance over time, to calculate the speed of sound in here. Remember, the speed of sound in a media is going to vary. And I just showed you that the speed of sound, or the speed of a wave is equal to lambda times f, or wavelength times the frequency. All right, so just keep it simple. Just keep it simple. I mean, just straightforward. Okay, so this is just an example. So if you're 50 meters from the canyon wall and you shout, so it's going to take 50 meters to go to the canyon wall, and it's going to take 50 meters to come back. So the total distance travel is 100, okay? And if it takes 1 second for you to hear it, so that means it's going to travel to the canyon wall, come back. So it's so it could probably take a half of a second to go and a half of a second to come back. So the speed is the distance. So this is not 50. So it would be the total distance would be 50 plus 50, right? So this is 50 plus 50, which is 100, and you divide it by 1 second. So the speed would be 100 meters per second. All right. So as I said, nothing. We haven't discussed anything new. I mean, I just gave you this formula, which you probably never. I mean, some of you guys probably have not seen before, but it's the same principle we're using. All right. So you have digested that a little bit. So I lied a little bit, okay? So I lied a little bit, but the speed of sound in a media is fixed. I say I lied a little bit, just a little bit. If you remember our first discussion, we said that speed depends on the inertia of a media, which is the weightiness, the heaviness, the bulkiness of a media. And it's also dependent on the elasticity of the media, the springiness of the media. Remember we said that? Okay. So this concept, what I'm getting into now, is a very important one. This is a very simple concept, but it's important. So the speed, we already gave you the speed formula, the wave formula. Speed is equal to lambda times f. But what I'm telling you is that the speed of a wave in a media depends on the density, which is the bulkiness of the media, the inertia of the media. So these are all saying the same thing, the bulkiness, the inertia. It also depends on the springiness of the media, the elasticity. The more elastic a media, the greater the speed. The greater the density, the slower the speed of the wave. The speed of a wave is also dependent on the temperature. The greater the temperature, the greater the speed of the wave. And that is why I lied a little bit, because if we have standard condition, the speed of sound in here is always going to be the same. So if you have the same temperature and pressure, the speed of sound in here is going to be the same. But on an extremely hot day, the speed of sound is going to increase a little bit, just a little bit, in any medium. And when we talk about the density, so the density is the bulkiness, the weightiness of a medium. The speed of sound, or as the speed of any wave, decrease when the density of that media is increased. For example, the speed of sound. So I'm talking. The speed of sound in here is going to be, everybody knows it's 330 meters per second. And when the sound hits, say, water, which has a greater density than here, it's going to slow down. It's going to slow down. The speed of sound in water is going to slow because of the density. So the speed of a sound, of any wave, once it hits a medium of greater density, it's going to slow a bit. If it hits a medium of less density, it's going to speed up. So you have to have that concept clear, because when we do ultrasound, the sound wave is constantly moving from one media to the next. When you start, it moves from hair to the skin. It moves from the skin to the subcutaneous tissue. Then it moves from the subcutaneous tissue to say the heart tissue. So it's constantly moving from media to media. If you know the density of the different media, you can have an idea of how fast the sound wave is traveling. But the general concept is that when sound wave hits a medium of higher density, it slows down. When it hits a medium of less density, it speeds up. Okay? And then if the greater the elasticity, the greater the speed of the wave. All right. So can I rub this thing off? Can I take this off now? All right. Let me just take these things off. All right. So we have that concept straight, and this is just going over what this is the speed, the wave formula. So we went over that. Speed is equal distance over time. The distance between one crest and one crest is the wavelength. The time from one crest to the next crest is the period. Period is 1 over frequency. So if you say speed is distance over time, and you just plug those in, you get your wave formula. All right. And then, as a wavelength of a wave is uniform, it's pretty so, and that is why the speed of a wave in a medium is fixed, because the wavelength of that wave in a medium is going to be fixed. It's not going to be changing. When you produce a wave in a medium, the wavelength is going to be fixed. The frequency, if what you set the frequency, is going to be fixed. So that is why the speed of a wave in a medium is a fixed number. Okay? However, as the wavelength of a wave in a uniform medium increases, its frequency will decrease. So say for instance, because the speed is supposed to be fixed, if the wavelength increase, the frequency has to decrease. If the frequency increase, the wavelength gonna decrease. And that is, so it's gonna do that to keep the speed fixed, because the speed of a wave in any media is a fixed number. We say that the speed of sound in soft tissue is 1540 meters per second. That's a number everybody needs to know. It's not going to change, and that's because if you increase the frequency, the wavelength have to decrease. What we also know that the speed of a wave depends on the properties of the medium through which it travels. It depends on the density, the elasticity, and the temperature to some extent. So this is another, you don't have to memorize the formula, but the speed, again, as we said, the speed of a wave in a media depends on the density and the elasticity. So this is the Young's this is the formula, that the speed is equal to the square root of the Young's modulus, which is a measure of elasticity, okay, divided by rho, which is the density. Okay, so as the density of the medium increases, speed decreases. As the elasticity increase, speed increase. As the density decrease, speed increase. As the elasticity decrease, speed decrease. Sorry. So this is a little formula that is good for you to have in your back pocket if you don't remember, what goes on when a wave travels from one medium to a next. However, simple thing, if the wave moves from one media to a more dense media, it slows down. If it moves from one medium to another medium, which is less dense, it's going to speed up. Okay? So it's a good formula to remember. So we also talk about the dependence of the wave speed with temperature. And generally speaking, the greater the temperature, the greater the speed of that wave. Okay? So speed is directly proportional to the square root of the temperature. Okay? T is temperature. All right? So speed is directly proportional to the square root of the temperature. And this Newton's Laplace law is basically we're saying the same thing that it said before, where the speed is equal to the square root of the elastic modulus, which is a stiffness. It'll give you some indication of the elasticity of the medium, and then rho is the density. All right. So the greater the temperature, the greater the speed. All right. So when we talk about boundary behavior, when we did incident and reflected wave, that is what we call boundary phenomena. When a wave strikes a boundary or an obstacle, it moves from one media to a next. So when you have one medium, you're moving to a next medium, the separation of them, that's what we call the boundary. Once a wave hits a boundary, a portion is going to be reflected and a portion is going to be transmitted through the medium. Okay? So again, it's going to be reflected. It's going to follow the law of reflection, that the incident wave or the angle of incident is equal to the angle of reflection. And it's going to be the portion that's going to be transmitted through the other medium is going to follow the law of refraction. So we talk about reflection. Now we go to refraction. When something is refracted, it means it's bent. When something is refracted, it bends. Okay? So when a sound wave moves from one medium to the next medium, the portion that's going into the next medium is what we call the transmitted wave. It's going to be bent. It's going to be refracted. So the refracted wave is always in a next medium, whereas the reflected wave is going to be in the same medium as I drew earlier. Okay, so at the end of the at the end of the medium, there's an obstacle, and you're going to encounter another medium. So a boundary is the interface of two media. Let me just draw it again. So if you're moving from, say, air, if you're moving from here to water, okay, and say this is here, M1 is here, and M2 says water, two different medium. So where the two media meets, that's what we call the boundary. Okay? I mean, if you put oil in water, you can see the boundary clearly because those two don't mix, so you can see a boundary. So that's what we're talking about. So if you have your incident wave, okay, so the incident wave is going to strike the boundary. Then you're going to have your reflected wave. So this is our incident wave right here. And this is going to be your reflected wave. It's going to obey the law of reflection. Okay, so this angle right here is going to equal to this angle. A portion is going to also be is going to come down here. So this is not a straight line. I shouldn't draw it like that. Let me draw it like that. It's going to be refracted. So when this incident wave comes here, a portion is going to go through to the second medium. So it's going to be transmitted. So this is your reflected wave. And then this is your transmitted wave, which is going to be refracted. It's going to bend. Okay? So your incident wave is going to be reflected. A portion is going to be reflected, and a portion is going to go through to the next medium, but it's going to be bent because the two medium have different density. When a wave strikes a boundary and it's moving into another medium, it's going to bend either to this way or it's going to bend this way, depending on the density of the medium in which it's now traveling in. So it's going to be refracted. It's going to be refracted depending on the density of the medium which it's traveling in now. So you see that the reflected wave is in the same medium as the incident wave, and the refracted wave is actually in a different medium. Okay? So as I said, don't try and complicate this. It's a relatively simple concept. And, you know, when you're doing ultrasound of any structure in the body, you're constantly moving from one medium to the next medium. So the wave, your ultrasound wave is going to be refracted, it's going to be reflected, depending on the density of the medium. All right? All right, so I know you got that concept. So let's move on. All right, so let's just move on. All right, so we're not gonna do that. So again, if you have an incoming wave, okay, if you have an incoming wave, when it strikes a boundary, it's going to be reflected and then go back. It's basically, um, we're not going to, we're not going to get into fixed end and free end reflection. We're not going to get into that. Um, we're not going to get into that too much. All right. So the observations that we made is that wave speed is always greatest in the least dense media, and explain how you get that. So when a wave moves from a more dense to a less dense medium, it's going to speed up. Wavelength is always greatest in the least dense media because since it have a greater speed, the wavelength tend to increase. So the wavelength is greatest in the least dense media. Frequency is not altered by crossing a boundary. So this is something you need to understand. If you transmit a sound wave through you're doing an ultrasound of the heart, the frequency that you transmit is going to be the same frequency. The only thing that's going to vary is the wavelength. Frequency is not altered by crossing a boundary. So if you use a 2 megahertz transducer to do your ultrasound of the heart, the frequency in the ear, the frequency in the skin, the frequency in the subcutaneous tissue, frequency in the heart is going to be the same. It's not going to change. So again, the reflected pulse becomes inverted from less dense to more dense media. The amplitude of the incidence wave is always greatest than the reflected wave. And that is because, you remember, wave transmits energy. So when you doing an ultrasound and you produce a sound wave, that sound wave is going to hit the structure that you're imaging. A portion is going to be reflected. So the greatest energy is when the wave incident, when it hits the structure. And then a portion is going to be transmitted through the medium that you're looking at, say the heart. So that incident wave, the energy is going to be split into a reflected wave and a transmitted wave. So the amplitude, which is a measure of the energy of the incident wave, is always greater than the reflected wave. Okay? Remember, amplitude measures energy and wave transports energy. All right. So the law of reflection, which we mentioned before, waves will always reflect in such a way that the angle at which they approach the barrier equals the angle at which they reflect off the barrier. Angle of incidence equals the angle of reflection. Change in direction of waves when they bounce off a barrier, that's so. And it's going to be reflected in the same medium. And so it looks like this. Okay, if this is your incident ray coming down, it strikes a barrier, is going to be reflected. This angle is equal to this angle, law of reflection. We went over that. So you have your incident wave coming down, it meets a barrier, it's reflected, this angle equal to that angle, but it's going to be refracted. When it hits the second media, it's going to be bent. It's going to bend up this way, or it's going to bend that way, depending on the medium, the density of the second medium. Okay. So so the law of so when a wave is refracted, it changes its direction as it passes from one medium to the next. And it depends, it's going to bend, the bending of the wave, it depends on the medium, the density of the medium to which it's now traveling. Okay? So, we're not going to get into any great sum. Just know that it's going to bend from one. It's going to the bending of the transmitted wave depend on the density of the medium in which it's traveling in. So it can bend this way, it can bend further up, or it can bend over there, depending on the density of the medium. So all waves obey these principles. And when you're doing an ultrasound of the heart, the wave that you use in the ultrasound is gonna obey these principles. So, if something is off, you'll get what we call artifacts. And these artifacts is because you're not obeying the laws, so you're gonna get strange images. All right. So again, refraction, the incident wave comes, it strikes a boundary, and when it enters the second medium, it's going to bend. It's not continuing in a straight line. It's going to bend. And the bending is dependent on the density of the second medium. Also, wave diffract. So we talk about reflection, we talk about refraction, and we talk about diffraction. So, so all waves obeys these principles. And when we talk about diffraction, waves have a tendency to go around corners, or they go through, if there's a boundary, they go around the boundary. Okay? And that is why we can hear someone, if we stand in wherever and someone is, say, at a little distance around a corner and they're talking, we can hear them because the sound wave diffracts around the corners and travel to us. So when we say diffraction, it is the change in direction of waves as they pass through an opening or around a barrier in their path. Okay, so if we're in the forest and the bird is whistling, the reason why we hear the bird chirping is because of diffraction. It move around the boundaries and the trees, and it change direction and all that sort of stuff, and we can hear it. When you're in, you must have observed that you go to you're in the sea, or you're on a pier, and if you're in a big boat, say you're in a big boat or a ship, and the ship creates certain waves, that wave that the ship creates, water wave that is, it can topple over small boats and it can do whatever. That's because diffraction. The larger the ship, the larger the wave of diffraction, and those waves can topple smaller boats. So the amount of diffraction increases with increase in wavelength and decreases with decrease in wavelength. So again, when you're in a big ship and it's moving, it's going to create water wave with very long wavelength, and that that can topple over a small boat. If you're in a very tiny boat and the boat is moving, it's going to create water wave with very small wavelength. It's not going to do anything. Okay, but diffraction is the change in direction of wave as it passes through an opening or around a barrier. So all waves observe these properties. We talk about all waves going to have a wavelength, it's going to have a period, it's going to have a frequency, it's going to have an amplitude, it's going to reflect, it's going to refract, and it's going to diffract. Okay, so you just need to have an idea of what these things is. And say if you have a wave and of a barrier, so you see the wave going around, okay, or you have an opening, the wave will go through. All right. Also, all waves interfere. Wave is going to interfere with each other. So, and the interference of waves is very important as well, extremely important. So when we say the interference of waves is what happens when two or more waves meet along the same medium. What happens? Two waves meet up. Okay? So a number of things can happen. The wave can add to each other. So we talk about positive interference, or the two waves can cancel out each other, and we talk about a negative interference. So when the phenomenon that occur when two waves meet while traveling along the same medium, that's interference. The medium takes on a shape that results from the net effect of the two individual waves upon the particles of the medium. So this is what we're talking about. So you have one sound wave here, and you have another sound wave. When they meet up together, if everything is lined up just right, say crest is on crest, crest is on crest, they meet up just so you have positive interference where the crest, the net result is a much larger crest and a much larger trough. So this is positive interference as opposed to negative interference. If a crest meets a trough and a trough meets a crest, they cancel out each other. So you'll get no disturbance. Okay? So all waves will interfere. Okay? You can have either positive or a negative interference. So remember that. All waves interfere. So the positive interference we call constructive interference. So two interfering waves have a displacement in the medium in the same direction. Okay? The upward or downward displacement, the medium has a displacement that is greater than the displacement of the two interfering pulses. So this is a constructive interference. You can see that the net amplitude of this resultant wave is larger than any one of these. Constructive interference. Okay? So two interfering waves have a displacement in the same direction, upward or downward. The medium has a displacement that is greater than the displacement of the two interfering pulses. So again, constructive interference, it doesn't, you don't have to have a situation where the crest is directly meeting another crest. It can be a crest meeting, a point right there, or a trough meeting a point right there. Okay? It's still going to be constructive interference. Okay? The net amplitude is going to be larger than any one of the two components of the interfering waves. Then you have destructive interference. The two interfering waves have a displacement in the opposite direction. So the medium displacement is less than the displacement of the largest amplitude. So this is what you have. So again, if a crest meets a trough and a trough meets a crest, they cancel out each other and you get no disturbance. But you don't have to have a situation where crest meet trough. You can have different points, meeting, and if it's an upward and a downward displacement meeting each other, there's going to be some amount of cancellation. So, but it doesn't have to be when you have destructive interference. You don't have to have no disturbance at all. All right. So when we say superposition, it's just when two waves meet each other. You can get some algebraic resultant. So again, if you have this wave meeting this wave, crest is not meeting trough exactly, so you get a constructive interference where the net amplitude is greater than any one, but it's not an exact, a twice or three times that type of thing. And destructive interference, again, you don't have to get no disturbance. You can get a little bit of disturbance when they meet, if the crest meet the trough, or some other point meets. All right, so we're gonna stop here. But those are the properties of waves, and you need to go over them because